everyone. Uh, Today we have Jeff Schneider, who I'm excited to introduce because he was also my advisor when I was at TMU. Jeff works in the intersection of machine learning and autonomous systems, and works in a variety of machine learning topics, but especially on reinforcement learning and Bayesian optimization. He has also deployed a lot of machine learning models in the real world, in government, in science, and in industry. So he was at the beginning of Uber's self-driving program. He's worked with the Department of Defense. He also founded a company on applying machine learning for drug discovery. And nowadays he works on nuclear fusion, which is what today's talk is going to be about. So take it away.
Great. All right.
Just say okay.
I need to say okay here.
Just say okay, I guess.
Okay, great. Thanks a lot, Kirti. It's great to be here talking to everyone. Let's see. So as you heard, I'm going to talk about reinforcement learning and especially in nuclear fusion. So really, this is going to be about the application with some methods thrown in here. This is a picture of me with my collaborators at ITER, which is the big tokamak under construction in France. I'll say more about that in a second here. Just to give you a background, these are some of my students and postdocs who've contributed to the work you're going to hear about. And but of course, we're all computer scientists. We're machine learning and AI experts. Our collaborators come from the Princeton Plasma Physics Lab, primarily, a few others in other places as well. So we rely on them for a certain amount of our plasma physics knowledge. I'll put this up. This is only the roughest of outlines here. Basically, I got excited about nuclear fusion, and I'm going to tell you why I'm excited about it. And then I'm going to tell you a little bit about our efforts to make progress in nuclear fusion that will somewhat randomly go over these topics as we go. So we'll just dive right in. So just to calibrate us all, I learned I need to do this because sometimes people don't realize this. So this is not nuclear fission, right? Fission is when you split uranium and you have a plant like this, and it does things like release radiation and sometimes melt down, and all kinds of bad things happen. However, these do produce electricity. So that's not what this is about. This is about nuclear fusion. This is about taking two hydrogen atoms and smashing them together into a helium atom, which releases energy. Why are we excited about this? Because we effectively have an unlimited source of fuel here on Earth. The energy density is higher than fission. But most importantly, there aren't radioactive byproducts. You just get helium and neutrons as your output. And safety is not an issue either. These things don't really melt down. They don't really explode. If you think back to your high school physics, whereas uranium just wants to fall apart, it wants to split if you get enough of it together. These two hydrogen atoms are protons. They don't want to go together, so there is no accidental release of energy here. And of course, what's the promise of this? If you think about all the, many of the grand challenges in the world, they're actually just energy problems. We have climate change primarily because we don't know how to generate energy without climate change inducing effects. Clean water, we don't have a clean water problem. There's plenty of water in the oceans, and we know how to clean it. It just takes a lot of energy. Same with food. We don't really have a food problem. We know how to do it, and we have plenty of resources. It just takes a lot of energy. So that's why it's exciting to think about how could you get limitless clean energy. How is this achieved? Well, the sun, those two hydrogen atoms that don't want to go together, the sun does it just with mass, right? It just by gravity, it forces them together. The only way we've done it here on Earth is with a thermonuclear weapon. You basically blow up a fission bomb next to your fuel, and the shock wave fuses it together. Not a great energy source for practical uses. You may have seen some of the hype around laser confinement. You get a fuel pellet this big, and you blast it from all sides with lasers. They've made some nice scientific advances there, but it's still well behind what I'm going to tell you about as tokamaks in terms of they're orders of magnitude behind where tokamaks are in progress for generating fusion. And so that brings us to tokamaks. These are the devices I'm interested in. What do you do? you get the plasma in the shape of a torus, and then you wrap the torus in magnets. So what's going to happen is that plasma needs to be hotter than the center of the sun. So you can't really physically keep it in place at high pressures and temperatures because it'll just damage whatever's touching it physically. So, but it is a plasma, so it's charged, and you can use the magnetic field to keep it in place. So these are big, complicated devices. This is one of them in the UK here. It's kind of a Where's Waldo puzzle. There's actually a dozen people in this picture, but they're a little hard to find. So very complicated devices, the tokamaks. So why is this not already done? Well, it turns out the dynamics of a plasma in a magnetic field like this is something called magnetohydrodynamics. It's sometimes described as what you get if you cross Maxwell's equations for electromagnetism with Navier-Stokes for fluid dynamics. The classic approach of physics is to use a lot of physics knowledge to design this physically as something that will have simple control loops in it. And then you can do single input, single output controls, often with proportional or PID controllers. That's the classical way. That's how we got to where we are so far with tokamaks. But of course, we do AI now. Machine learning's made lots of progress. We actually know how to learn to control complex nonlinear systems, even those that have poorly understood and unstable dynamics. That's the opportunity we're faced with here. And of course, the challenge is the tokamak is a real expensive device. We're not going to get a lot of time on this device to run our the same thing that solves half cheetah with reinforcement learning is not going to be effective on a tokamak.
Just a quick question.
Yeah.
If you somehow lost control of the magnetic field, that seems like it would still be kind of bad.
Well, it's
something would melt.
Well, it's kind of bad.
Okay.
What happens is if you the plasma will leak through the magnetic field even when things are going well. When things are not going well, it'll leak through fairly quickly. And it has enough energy and momentum that it'll slam against the walls of the device and it'll damage the device. But it's not, it's not catastrophic. Nobody's going to get hurt. You're just going to have to turn your device off. Yeah. Okay, this is the one we primarily focus on. This is the D3D tokamak. It's in San Diego. It's run by General Atomics. It's the largest one we have in the United States right now. I'm going to get to methods in a moment, but just to sort of preview, because the immediate thing, okay, you want to use reinforcement learning, you want to do what are you talking about anyway? So just to give you a preview, the kinds of states we're interested in here. Some of them are scalars. What's the strength of the magnetic field, the inductance, the current, and some of them are what we call profiles. So you'll see some of these profiles, what it is. This is a cross-section of the torus. It's assumed to be colloidally and toroidally symmetric. So it's assumed that if you measure one of these quantities across a line here, that you, to first approximation, captured the full state of it. So many of these things like rotation, temperature, density will be given to you as a 1D curve. So here's a rotation profile. It's rotating faster near the inside of the torus than near the outside. So just to give you an idea what's there. What can you do to this thing? There's a bunch of things you can do to affect it. One is, I mentioned the plasma leaks out even when things are going well. So what you have to do is inject more back in. And by doing so, you affect the dynamics. You can choose the amounts and the direction you inject it. You can also pump gas into it. And you can do some things with inducing current with solenoids. And you can also change the shape of the cross section. You've got all those magnets there. And if you change those magnetic fields, you can change the shape of the cross sections, which also changes the properties of it. So just to give you an idea of the kinds of states and actions we're talking about when we think about reinforcement learning or other kinds of approaches. Did I see a question? Oh, okay.
I
think it's from the Zoom.
Zoom is
the way to
Oh, maybe it's a hot mic. Okay, we'll see. So just to give you an idea, when you run these things right now, they're not steady state. You run a shot on D3D, that's about 6 seconds. What it does, this is the plasma pressure here called beta N. It starts near zero. You do some ramp up, or usually some kind of open loop recipe. Maybe first turn up the density of the plasma in there, start to heat it, start to induce a current in it. There's a whole recipe for ramping up. The idea is to arrive at something called flat top here, which would be the steady state operation of the tokamak. And then it's not shown here, but then at the end you have to shut it down as well. These are milliseconds, so this is about 6 seconds on D3D. So that's what a shot looks like. And I'm going to give you a little bit for beta N, just the numbers here. Just to give you an idea, because I'll refer to these as a little bit of a performance metric for us. 2 is something that research tokamaks routinely run at for the plasma pressure there. There's lots of ways to get there, and we can run there, but we don't. It's still a research problem of how to maintain it without any disruptions for a long period of time. Going as you get up towards 3 or over 3, now we're more in the range of, yeah, it's happened before, but it's very unclear the best way to get there, and you can't really even reliably produce those kinds of shots. So just to calibrate you on that performance there. So here's just to put the context of the work I'm going to tell you about in with the other things going on in the world that you may or may not have heard about. Okay, we don't, right now, the tokamaks, we can run them. We don't get out more energy than we put into a tokamak right now. So what are the things you can do to get more energy out of it? One is you can just scale it up. The power you get out scales with plasma volume. That's what ITER has done. This is under construction in the south of France. It's such a large site, you can see it here, that it's been under construction for 20 years, something like that. And estimates are still sort of 5 to 10 years away. It's taking a long time. There are real questions about whether and how successfully this will be finished. Another thing you can do that's kind of cool is it turns out the power input scales to the 4th power of the strength of your magnets. So if you can make stronger magnets, that gives you a real leg up. Commonwealth Fusion is one that's taken that approach. And so you can see their site is smaller, their device is smaller. You can actually see the people in this picture. They're trying that approach. I mentioned the plasma pressure. The power you get out scales quadratically with the plasma pressure. So that beta N is the normalized figure. It's the ratio of your magnetic pressure in versus the pressure of the pressure of the plasma going out. And so that's where we're working. These things involve massive construction projects. This involves doing AI and software. So you can guess which one we picked, and any wins here can then be applied to those. So that's where this work fits in the area of trying to improve the story for fusion. So what are we going to do? We have reinforcement learning and Bayesian optimization algorithms. We want them to operate this tokamak device here. This thing's expensive. We tend to get, in my lab, we would get 1 or 2 3-hour sessions a year to run on this real device. And so most of our time is going to have to be running against things like data-driven dynamics models and first principles simulators. So that's the strategy. We want to figure out how to and so I'm going to, this picture looks busy, but it's actually a simple picture, and I'm going to use it a little bit to organize the approaches we take here. And so the columns of this picture are whether you're using feed-forward control, meaning when you go to run the device, you're just going to submit a whole trajectory of commands open loop and just execute them blindly. Or are you going to run a feedback controller, a closed loop system that constantly senses the state, chooses a new control? So those are the columns here. And then the rows are we going to, and these terms I'll use a little bit loosely here, but are you going to be model-based? Are we going to have some simulation model of a tokamak that we can practice on to try to come up with our policy and then deploy? Or are we going to do what, again, loosely speaking, I call model free, in the sense that we don't have a dynamic model other than the tokamak itself? We're going to have to do the experiments on the tokamak itself. So you can think about all the combinations of these approaches, and that's kind of what we're looking at. So I'm going to start with this, where we're doing feedback control, and we're going to have a model that we can run on. So this would be your standard sort of reinforcement learning setup to this particular problem. Okay. Now, as I mentioned, of course, the true environment's too expensive, so we're not going to be able to train on that. We've got to train on something else. So you might imagine, well, let's use a simulator. Turns out there are such simulators. The physicists know the first principles. Of course, it's just quantum mechanics. So there are simulators, you can run on them. And you can learn control policy that way. And if you do that, sometimes good things happen. Those of you who saw the DeepMind Nature paper saw one example of that. They looked at just controlling the magnets to control the shape of that profile of the plasma inside the tokamaks. It turns out the first principles for how the plasma reacts to the magnetic field are well understood and accurate. And so they were able to do exactly that. Run reinforcement learning on the simulator, put it on the real device, it works. Life is good. It turns out that, well, because the simulator and the models are good, actually the magnetic control of the shape is mostly a solved problem already anyway in tokamaks. However, there are lots of other control loops in the tokamak for which the simulations are not accurate. It's the simulations are computationally expensive, and even if you can afford to run them, they're just not accurate enough to use that strategy. So we're going to have to do something a little bit different here. Let's see. Oops. Let me. Yeah. Sorry. I'm just. There are a couple of references here. These are some things in the nuclear fusion literature that our collaborators published, just comparing the accuracy of the simulations on things. And so that's not going to work for the control loops we're interested in on the real device. So what are we going to do? We're going to set up what's basically an offline reinforcement learning problem. Although we don't get much time on the tokamak, over the decades, it has had lots of shots run, and all that data has been stored. And so we can take all that data and run an offline reinforcement learning output. Great. I will skip the model 3. I will just note one thing about the offline RL setups. Many of us have worked in this area. There are many common benchmarks for that. Many of them are not relevant for real problems because the primary one is a lot of the benchmarks are deterministic systems and or fully observed. And so the tokamaks are the combination of stochastic and partially observed. So the algorithms that work good on those benchmarks don't necessarily work so well. Tokamak. And of course, the other one is you can't really behavior clone this kind of data either, because everyone who runs an experiment on that device has a different goal. There is no singular goal that you can just copy that behavior. They're all testing different kinds of physics and different ideas. Okay, so what are we going to do? We're going to go ahead and learn a dynamics model from the data. We're going to download 20,000 shots from the database from D3D. We're going to learn the dynamic model using those states I mentioned early on. And then we'll learn a policy from that model. I think most of you are familiar with some of the algorithms for offline reinforcement learning. We're going to use similar algorithms there. There are some differences, and those are the things that I just mentioned. The ones in the literature being deterministic versus stochastic and partially observed. Okay, so how are we going to get this to work? So the traditional offline RL algorithms tend to use versions of pessimism as their main way to just keep you inside the data support and have you continue. And so, but in our case, because of the differences I showed you before, we're going to have to do a little bit better than just be pessimistic and do what's in the data set and not stray too far of it. We're going to need well-calibrated uncertainty in our model. And then we're also going to need the policy learning algorithms that use that well-calibrated uncertainty as best they can. If you think about it, just being pessimistic and staying close to the data produces exactly what you would expect it to produce, something relatively close to behavior cloning. So we can do more than that if we have a real understanding of the dynamics of our system, especially the uncertainty.
You know, all this data that's been collected over the years, is there some general sense that sort of probed all the states and so forth that system could ever reach?
I would say there's a generalist sense that it has not even come close to that.
Okay.
Yeah, the number of variables in the device versus the number of actual experiments can.
So what does that mean then for this whole framework? You know, if we,
Yeah, I think what that means, and this gets to, this is a great question, because when we started, we thought we were going to use the simulators. In fact, that's what we wrote in our first grant proposal. We're going to use Bayesian optimization to run experiments on a simulator. I'll see it run it on the device. What we learned when we did that is the simulators were never intended to be used the way we think about simulators, where, okay, here's an open field, give me any control sequence you want, and it'll let you know what happened. That's not how they use them. They use them in order to replay shots that have already happened, where they fill in the full trajectories of many of the variables and have the simulator fill in the missing variables so understand better. But if you use it in the way we would like to use a simulator, it just diverges immediately. And partially that's because the data comes nowhere close to covering the space. Yeah. Okay. Let's see. I will just to give you a rough idea of what we used for this. What we converged on now is an ensemble of RPNNs. They make predictions at 20 millisecond time steps. We use, this varies depending on the effort, but 15 to 20,000 shots from the database. If you multiply 15,000 shots by 6 seconds at 20 milliseconds, you get a few million data points. That's what goes into our dynamics models, and we'll train multiple ones of these. So, and then of course we do the usual thing. We use these to roll out shots. You should get your epistemic uncertainty from the ensemble. So every time you want to roll out a shot, you draw one member from your ensemble, and then you use that to roll out the whole shot. But then in each time step of the shot, you'll sample the Gaussian that's predicted here to give you the aleatoric uncertainty that happens when you device. So that's the idea. That's how we're going to use this thing. I want to take just a quick side note here. The topic of bootstrapping is in the literature. In statistics, we understand bootstrapping well and why that's used to represent epistemic uncertainty. In the machine learning literature, things are a little bit all over the map on people's feelings about this. So again, what you're trying to do is get from your ensemble of models uncertainty about the underlying function. And the way you do that is you take your original data set, you resample with replacement to get lots of different data sets. You train your model on each one of them, so you get now a whole distribution model. And then point-wise, you can go through all your models and turn that into a distribution of the epistemic uncertainty about the underlying function. What's amusing is the machine learning, the statistics literature, I would argue, is relatively clear on what they think about bootstrapping. It's well understood. There are theorems. This is somehow the right thing to do. Machine learning literature is all over the map. There are some that say, why aren't they better? It hurts the accuracy. There are others that say, you don't really need to do it, and they mix epistemic and aleatoric uncertainty together and say, oh, that's a good thing. And there are applications that some use it, some don't. It's sort of all over the map. So we said, okay, wait a minute. Does this matter or not? Do we need to do bootstrapping, or Or can we just rely on, like some of the papers do, random initialization of weights and the randomization in choosing mini batches? Is that enough? Are we okay? Don't worry about this. This is just, we ran a ton of experiments varying lots of things. The result is not that surprising. So here's just an example of a sine function. We sampled some data. We ran all these. What happens? And then we ask for 95% confidence intervals on the underlying sine function there. And through lots of experiments, what we saw is that the coverage you get if you run bootstrapping, some of the other variables are there, but we tried lots of variables. You get things around the confidence level you want. If you say, oh, don't worry about it, I randomized the initialization, I got random mini batches, everything else, don't worry about it, just run it. You get things like that, right? Your actual uncertainty quantification has nothing to do with your actual uncertainty about the function. And so we're now continuing to work on, okay, but what happens when the dimensionality goes up, the capacity of your network goes up, or there are the other conditions for bootstrapping to hold in terms of its convergence and what limits of what variables. We're exploring all those things now. But just a quick take-home message. Use bootstrapping when you're taking these kinds of approaches. It's the right thing to do, and it actually matters for what you get. There are a few checks there. Your function has to be converged. Your learning rate has to be reasonable. There are things you have to do, but it's important to do this. Okay. So I just said it's important to do this. And I justified that by showing you the coverage and saying one of these has the right coverage and the other one coverage. But, well, does it really? Maybe it doesn't matter. Just run your offline RL algorithm, get some noisy samples, train a policy, whatever. Who cares? I'm sure it's fine, right? And so we said, okay, well, let's think about this. And even the way this is sampled, there are some papers that don't sample an ensemble member once per episode. They do it once per time step. Yeah, things are all over the map, but surely it doesn't matter, right? Okay, the way I think about epistemic uncertainty and aleatoric uncertainty, usually you talk about epistemic as the uncertainty that can be reduced and aleatoric as the uncertainty that cannot be reduced. The way I think about those uncertainties is epistemic uncertainty is the one that's temporally correlated in time. And aleatoric uncertainty is the one that's temporally IID. I think that's the relevant feature of those kinds of uncertainty. And you can think about that in terms of driving a car. I also work on self-driving cars. And so you can think about what happens if you're driving a car down a narrow bridge and you just close your eyes. Well, you might think, I can probably do that. My errors, if I assume they're temporally IID, my deviation from the center line is going to grow with root t. I can probably close my eyes for a while. Nothing too bad will happen. But of course, that's not the reality, right? At the moment you close your eyes, the steering wheel is in a certain position and it has a certain error, and your deviation from the line grows linearly with that, and you drive off the bridge much faster than you would if you think you're in this scenario, right? So this matters. Okay, it matters for cartoons, but that doesn't matter for real things. Okay, so I want to point. This was in a NeurIPS workshop paper from a couple of years ago. What we did, this is a different model than the one I just described of sampling an ensemble of RPNNs and then sample the from the Gaussians there every time step. We did something a little bit different here. What we did is train the same RPNNs, but then rather than sample that Gaussian, we trained a Gaussian process to represent the error between our prediction and the real function. And so what that meant is we can get correlated error predictions for our model. So whereas if you just sampled the RPNN to sample this whole function, you might get something like this yellow curve for the error between your prediction and the truth. But if you sample the GP, because it has its correlation from the kernel, you get a smooth sampling of that error between your model and the ground truth. And so there are all kinds of, you can read the paper, there are all kinds of tricks. How do you train that GP to actually match the error statistics of the model you just trained? That's what's worked out in the paper. I'm not going to go through those now. But we went ahead and did that. And this is this slide's got too much stuff on it, so I'm just going to say what the punchline is. What the punchline is, if you then take that model, which is in some sense correctly modeled the temporal correlations in your model error, and you train a policy on that, rather than just saying, "Oh, don't worry about it. I'll just sample from the noise. I'm sure I'll get something robust." The result of that is that across, the fusion example that we run, and then some of the toy problems, cart pole, and some mountain ones, you actually get better performance in the policy that you trained by correctly modeling the temporal correlation in your model errors. So I'm going to skip right past that, but this is also very important when you're trying to learn how to control these physical devices that you have poor models for.
So, is the effect of this to make the uncertainty larger? So, when you apply pessimism, you're being in an even more constrained region. Is that one way to think about it?
That's one way to think about it. It becomes larger. It's in the same sense as that car driving example.
Right. Yeah.
If you don't have the errors correlated and their IID, just the kind of back and forth on average, it sort of cancels itself out, and it's like a random walk. You grow with root T, but when the errors are correlated, whatever error you have, that exact same error builds up over time. And yes, what happens is if you do it wrong, you end up with a policy that's not conservative. And in fact, what actually happens with the offline RL algorithms you have, because they have this issue in them often, they just tune the other heuristic parameters to make them much more conservative. Like many of the offline RL algorithms, even the model-based ones, they chop their rollouts. Some of them chop their rollouts down to literally a single time step. Because if they do more time steps than that, the policies just are not conservative enough. But if you model the error correctly, you don't have to do that, and you can actually get a better, more robust policy. Okay. Yeah, you can look up the paper if you're curious about that. Let me jump back now to, okay. So let's get on to this model we've been training and how things are going here, just to give you an idea how bad it is. These are two different data sets. This is a data set that you get by post-processing the data on the tokamak after the shots ran. This is the data that you get online, which you need for closed loop control, because that's what's available at the time. These are explained variances. So if you look at the variance of the test set versus the variance in your errors, you get your percent explained variance. So the post-process one, we can get about 55% explained variance, which is really not great. People don't really write things like that in papers. They're not really proud of numbers like that, but there's some signal there. If we look at the data that we actually have to run the closed loop controller from, that drops to like 20. And so just to give you an idea for the challenge of the problem. Okay, but nonetheless, I showed you this picture before. Nonetheless, these actually are samples from our model trained from this. The dotted and dashed lines are what happened in the shot. So this is a shot we took from the test set. It wasn't in our training data. And then we fed in all the actions for that shot and asked it to roll out what happens in these states. And you can see reasonable things happen. It's not perfect, but reasonable things happen. And what I don't have here is what this looks like if you try to run it in one of those simulators. But like I said, they just diverge. This is well, I won't worry about this. This is an unusual shot. You don't usually run things like this where you turn it up and down twice, but again, you get reasonable predictions from these shots. Okay. Now, I want to tell you just a little bit about what happened when we ran this thing on the tokamak. We did a couple of things here. Don't worry about the pictures. These are going to be a bunch of physics quantities, but we tried to control two things. One is that plasma pressure, that beta N that I mentioned earlier. Usually you want to try to get that thing as high as you can, but at minimal, you want to track whatever target you have. This is something called differential rotation. Don't worry about the details, but basically the plasma is not static in the magnetic field. It's rotating in a spiral around the torus quite quickly. And the properties of that rotation are such that if you can create differentials in that rotation, it helps you with the stability. So we'd like to be able to do that too. Okay, so what we're going to do is we're going to go ahead and do that. We've trained our model. We're just going to run PPO on the model that we've trained, and then we'll run that on the real device. So a couple of references here. You can read about these from L4DC and another arXiv paper. I like to put this picture up because this is the control room for the D3D tokamak. It looks like a little mini NASA or SpaceX control room. What's exciting about this picture is this is Ian. He's my first PhD student on this project, and he's the session leader, so he's running the experiment. All of these guys are plasma physicists who are helping him operate the device, and virtually always the person sitting in this chair is also a plasma physicist. And so Ian, I believe, is the first what we would call an AI person to sit in that seat. So that was very exciting for us to do that. What happened? So we did some of these feedback control things on the device. We controlled some of the actuators that mentioned here. The dashed lines are the targets for beta N, and you can see we're trying to get up here in the range where things might start to be a little challenging, going over 2 here. And you can see that things moved kind of in the direction we were hoping. So it didn't blow up. That's nice, but probably we can do better than this. We also had some actuator problems. This I'll show some more of these plots, so I just mentioned this. This plot on the right is literally just showing what we commanded the actuator to do and what it actually did. Sometimes those don't match up, and that's a different issue.
Yeah, I was wondering about when you went to run these experiments, like what kind of safety levels or like safety layers were put in place on the device?
The device has various safety things in place that will invoke a shutdown if the control's not going well. But on average, it's not a huge deal because it is a fairly robust device. If we really maxed out beta N and then immediately disrupted and slammed all the plasma against the wall, that would be bad, mainly because all the physics folks at D3D would be, thanks, we won't be seeing you again. But nobody's going to get hurt anyway.
Yeah, I'm like quick follow up. I'm just curious, like the process of convincing the plasma physicist it's like okay to put a neural network.
Yeah. So there's a whole proposal process separately from the grant funding process to ask for time on the device. So you tell them what they're going to do, they review it, and they select some of them. Then there's also like a code check and I don't know, you might call it like a bench test. They run it without the tokamak attached. So there's a few hurdles you go through to make sure it's not crazy. Some other results. This is the differential rotation I mentioned. Again, you can squint and say things are going in the right direction. That's maybe. Here is after we made some improvements. This is beta N tracking again. This is after we made some of the model improvements that had to do with the model architecture, the time steps involved, and a little bit how we did the uncertainty. This is beta N. The scale's not well, but and this is a different scenario. This one's called a high colloidal beta. You can see here the ramp we're trying to track for beta N, and it goes pretty well until you get almost to 2.5, which actually pretty good. It's definitely better. Around this point, something happened with the actuators again. We were asking for more, and they said no thanks. And so that's a different part of the issue, but also an important one when you're dealing with real devices. But we're certainly getting better at the closed loop control for these devices. Okay, so after that round of experiments, where does that leave us? Well, you know, we were the first ones to put fully closed loop reinforcement learning based control on the real tokamak for these control loops. We eventually were able to establish some reasonable control for them, but we clearly still have some work to do in sort of policy learning improvements and how we manage the uncertainty. And so we did a couple of other things here. Now I'll just mention some of these things quickly here. So we were operating in this domain here where we're doing closed loop control. If you see how the simulations worked, it does sort of beg the question, some of these variables, we can actually command open loop and some reasonable things will happen. So that's essentially what we're going to do. We're going to take that exact same simulation we have, and rather than run RL policy, we're essentially going to run a planner on it. You can use, you know, CEM or some planner or some, you know, whatever method you like, but you're essentially running a planner to find a control sequence that you're going to run open. Yeah.
So just going back to this previous, when you're controlling a tokamak, what type of time scale are you looking at in terms of, you know, how fast you need to be able to control the system? And
yeah, the time steps here are 20 millisecond time steps.
And your policies can adapt to 20 milliseconds.
Yeah, so it means basically you need a feed forward pass on a neural net, and you probably can't afford to do much more than that. Our collaborators do a version of MPC, but it's literally they pick 3 candidate controls and simulate one time step forward and just pick the one of the 3 that's the best. That's about the limits of what you can afford. Okay, so here we go. We'll just do this feed forward. This says what I just said. We're going to run a planner on our model rather than a policy learner. We're just going to get an open loop series of commands. And it turns out this is the result of us doing now not only single beta N control or single differential rotation, we're actually simultaneously trying to hit a beta N target, which is here, not an especially high one. This is like 175, but the red one here is what happened. Sorry. When you run these experiments, you virtually always take a reference shot, which is a historical shot from the database. And all the things you're not going to control, you just copy all those controls from that shot, and then you manipulate the ones you're going to control. So this red one is what the historical shot did, and this blue one is the result of ours. You see, we actually hit this target pretty well. The differential rotation, we did not reach the target here. In post hoc analysis, we realized we didn't have the device didn't have enough power to actually make this target, but it did the best it can. And we also maybe didn't trade these two off, the weights on these as well. But interestingly, doing feed forward produced a much better, more reliable result than the feedback result. So, okay, let's think about that a little bit. That's a little puzzling because feed forward, right? You don't even get to watch the state. How do things go better? There must be opportunities to do better closed loop. And what's interesting is some of the loops we replace are actually usually run with a PID controller. And so that is maybe humbling to say that. And so we asked ourselves, well, what is a PID controller? What can we learn from that? And so I'll just make a few comments from a NeurIPS paper from where a year and a half ago. We basically asked exactly that question. We have these conflicting challenges. We have a sim to real gap. We know that one. We're also in a partially observable setting. We're going to have to do things about that. The usual thing would be to look at history, which we do. We have an RPNN. What is going on? What can we learn from the PID controller that can help us out? And yeah, that's just the history here. Okay, I'll skip these. So for those of you not familiar with a PID controller, it's one that would traditionally be a single input, single output control loop. And what you do is you have a target you're trying to track, and you measure your current error from that target, the integral of your error over time in tracking that target, and then the derivative of the error signal. And you just put a coefficient on each of those and add them together, and that's your control signal. So very simple, but it does have a certain adaptability. It doesn't even have a model, but it does adapt to different systems pretty well, right? Because of that thing. So this says what I just said. You look at your current error, the integral of your error, and the derivative of your error, and that is the controller. So the obvious question is, okay, well, maybe our features just weren't that good. We should make those be features. And so we did that. We called that the PID encoder. We just took our observations and tacked on the PID terms for our tracking term. And then we have a neural network, a policy there that has those things. Let's just train that policy. That should be better, right? Then we said, well, okay, but maybe we can do a little bit better than that. And so actually, I'm short of time, so I'm just going to skip to the end. What we did is just created an architecture, including attention as well, that more generally adds in derivative terms and integral terms into the architecture so that all of those are available for the policy, regardless of whether they're specifically the tracking error terms or not. And so if you put this together for your policy network, then you have a much more general thing that has some of the features of that annoying PID controller that's so simple and yet often does quite well. But just as a reminder, one of the reasons we can't just go back to that is PID is originally designed as single input, single output. People put them together for multiple input, multiple output, but it's a real design problem how you do that at all. And we really want to optimize the joint connection of all these actuators and states. Okay, so let's see. Again, I'm short of time, so you can read the paper if you're interested. What I'll mention is that that last version does quite well. It does well in our simulator, in our fusion simulator. We mixed a theoretical simulation from the literature, our data-driven simulator. We cross-trained one for the other. This latest model performed quite well. And then what we said is, well, let's just make sure we didn't overfit this to fusion and make sure this is something that's actually useful. So there's a whole set of these benchmarks we're all used to seeing that are the partially observed versions of them. The P's are you only observe the positions, and the B's are you only observe the velocities of all the state variables, and then you still try to control the device. And what we were able to show is that our algorithm actually outperformed many of the other things in the literature to solve those kinds of tasks. So there is something really nice from the insight from the PID controller there. Okay, I'm going to just keep moving here. Still, these are all based on models, and it's just hard to get good models. We did our best with uncertainty quantification. Maybe there are some things where there just isn't any way to do it other than to run experiments on the real device. And so we said, okay, let's try it. What can we do on the real device? You guys are familiar with Bayesian optimization. The most straightforward thing you can say is, let's plow blindly forward. We're going to run Bayesian optimization on a tokamak. I think I'll skip this. I think everyone's familiar with this black box optimization or zeroth order optimization of an unknown function. The key challenges is we're going to have a fairly high dimensional space. We may need to represent the current context, the current state of the plasma, and our number of experiments are going to be numbers like this, which usually you wouldn't really want to see those numbers in a Bayesian optimization problem, especially if it's high dimensional. But nonetheless, we're going to run this. We actually used a pretty simple acquisition function, generate an action, run it on the real device, observe the data point, including the objective criterion of how that provided, do the posterior update, you have about 15 minutes between shots, so you can do that. Yeah.
So is this a single objective application or multi-objective like you're looking?
This is, we heuristically combine the multiple
Okay.
so that we get a single objective. Exactly. Yeah, we'll do a posterior update. Again, the shot is 6 seconds, but it takes about 15 minutes to reset the. So you've got enough time between the shots to do a full application. We did that. And the one thing we did, the first example I'm going to show you is in this category, less than 40 data points. The way we addressed that was we actually we have all the data from the historical data. We can at least pre-populate our model with the historical data. So we're not starting from zero, right? If you start from zero and run UCB, you're just going to get a tour of the vertices of your space, right? And it's going to be completely useless. But if you pre-populate it with some data, you can avoid that. The part of the problem we worked on, I mentioned ramp down before. Ramp down is important too, because it's like riding a bike. When you're riding a bike at speed, it's so stable you can take your hands off the handlebar if you want, right? And it'll go straight. As you slow down to stop, you have this problem. None of us have a problem with this now, but when you're a kid, it's certainly a problem. The slower you go, the more unstable it gets, right? So you're trying to keep the thing stable until you get slow enough that you can just put your feet down. It's the same thing with the tokamak. At some point, it's getting less stable. It's going to disrupt, and you just want to get the energy down as far as possible before the disruption happens. So that's the problem we tackled. This is the parameterization. There's ramp down recipes, just like ramped up recipes. We parameterize that into a 9-dimensional Bayesian optimization problem. Don't worry about this. This is the physics speak for what I just said about trying to get the energy down before the thing falls over on you. And we went ahead and ran Bayesian optimization. The reason we were able to get 40 experiments is basically because most experiments concern how you do the ramp up and the flat top. And by then the experiment's done. And so aside from don't damage our device, they don't actually care what happens during the ramp down. And so that meant we could piggyback on their experiments and do a few more. What we did is over time, we ran Bayesian optimization on this again, 40 experiments, 9-dimensional space, not something you would normally do. And we got a nice physics result, which is the recipe, the human designed recipe changed the elongation of that cross section. It trades off how easy it is to keep the plasma vertically stable versus how easy it is to have an internal stability crop up. And it turned out the human generated recipes were actually doing this wrong. They were overthinking it. And the best thing was to not do that. That's what we discovered. 9D space with 40 experiments. So that was pretty cool. We got a factor of 2 to 5 reduction in the energy at the point where the plasma is disrupted. So that was pretty cool. So we said, okay, let's do more. It works for ramp downs. We're going to do something else. This one is called electrocyclotron heating. Basically, you can shoot some microwaves into the plasma, and it heats the plasma, and it preemptively can stop some of the instabilities that happen in the plasma. But the problem is, what is the shape of this beam supposed to look like? It can be multimodal, and you have to decide where to shoot it. That's the Bayesian optimization problem. And unfortunately, because this happens during ramp up, now we're in this regime, less than 10 experiments. Okay, nobody runs Bayesian optimization with 10 experiments. What are we going to do? We're going to use the historical data, like I said. But the other thing we're going to do is we're going to say, okay, well, let's just stretch this out a little bit. We do have this dynamics model. We could bring this to bear on it, and that's exactly what we did. So I'll skip the details of the variables. They're variables similar to the ones we've been talking about. We used the past data that I mentioned. But then what we did is we took that dynamic simulator, and for every we had to do this offline in advance. For every candidate the Bayesian optimization was thinking about in advance, we ran that through the dynamic simulator to roll out the shot and estimate how good it did at preventing those instabilities. And then we turned that prediction into the prior that the Gaussian process was using for Bayesian optimization. So again, if you run 10 experiments of Bayesian optimization, traditionally, what's it going to do? You're going to get a tour of the vertices, right? How do you make it not do that? That's with a traditional flat prior that you usually have in a GP. How do you get it to not do that? You have a prior that actually tells you, hey, those vertices probably aren't good, and that focuses your experiments. And so that's how we were able to run this. I'll skip that stuff. The result was pretty amazing, actually. We took a reference shot. This is something called a high Q-min scenario. In the database, 10 of 12 shots disrupted when they had this. And in fact, on the day when they set up the device, the first thing they do is reproduce the reference shots. They did 2 reproductions and they both disrupted. So now we're up to 12 out of 14 of these things. If you just run them out of the box, they're going to disrupt. And then we had our experiment, and 6 of 8 of ours we were able to run without disruption. Again, hard to do much statistical analysis on that, but it actually is statistically significant in this case. It's quite a bit of difference. But the exciting thing is, this is beta N that I've been telling you about. By the end, we were almost up to a beta N of 3.5 without getting disruptions, which actually is a scientifically challenging thing to do. And so this is something we're now in the middle of writing up here. We've since, our collaborators got excited. They ran this in Korea as well on a device called K-Star. I'm going to skip that because I'm out of time. And I'm going to tell you a little bit about, oh, I'm way out of time. Okay, sorry. I'm going to skip ahead faster than I thought. We're doing a bunch of stuff with LLMs, using them as domain expertise, right? The big thing we learned is that, yeah, you can do these data-driven things. That's great. But it turns out, no shock, physicists actually have learned something about tokamaks and plasma physics all these years. But we're struggling to find a good way to mix the two things together, and we're investigating LLMs to do that. So a lot of cool work there on making an LLM-based shot designer that simulates shots, allows you to give feedback on them, improve the shots. Going to scroll ahead on that because that's still work in progress. For future work, I wrote probably not feasible for tuning a feedback controller online on the device, but actually I think it's possible. I think being careful, there are things similar to that, right? There's meta RL, there's other things. It's not completely crazy. So at this point, we've run a bunch of different machine learning algorithms across many scenarios. We've had some scientifically good results in terms of ramp downs and using ECH to suppress tearing modes. And here's my take-home message for everyone here. You know, the classic approach, and this is how nuclear fusion has been done as well, is the single PI who comes up with a single hypothesis, gets a single experiment on the tokamak once a year, and then analyzes the data from that single run, and then goes back and repeats that thing next year. And that's very much the way nuclear fusion research still happens. Of course, in this community, this isn't shocking for me to say this, but this is, you know, in the science in general, this is a transition that's still happening, right? Once we're getting AI assistance, we want to simultaneously look at all the data, consider all the hypotheses, and run lots of experiments. So it's really time for the scientific community to think harder about what does it mean to do AI at scale? How am I going to give a large number of experiments? You're not really meant to run an AI algorithm the way I did. Here's your 3 hours for 2025. See what your AI can do. That's not really the way AI works, but we have the methods. We can make the improvements. And if we do this at scale, we can really move science forward faster. And just thinking bigger, that's what I'm excited about for science in the larger scale of things, not only. So sorry, I talked a little too long, but thanks for your.
Thanks just for the talk. There are questions.
The question sentence last part, and then, so I forget what you call it, but designing
Oh, yeah.
the shot or whatever. I guess, we could imagine that, put AI system, LLM, designing these things, and then, there is a physicist who said, okay, that's a proposal. And then this LLM sort of explains the rationale behind what it's doing. I mean, do you imagine that interaction?
Yeah, that's exactly the idea. I drew a closed loop on here. So the idea would be that the physicist would type in and say, hey, I'm interested in a high Q-min scenario. Would you generate a shot for the high Q-min scenario? I'm trying to reach a beta N of 4. Would you generate that shot? And then what it would do is say, oh, okay. It generates the controls. It uses our learned dynamic model. And then it generates all the curves for what that shot would look like. And then the physicist can look at those curves and can say something like, just like you would when you talk to ChatGPT, you can look at that and say, oh, that's great, but actually that's plasma current's too high. That's really not going to work for what I had in mind. Would you do it again and don't put the plasma current over this limit? And then it would go around. And so that's the idea, that you would have this interactive design loop. But for the data to say, for purely data driven to say, don't put the plasma current so high. I mean, what's it going to do? All right, I'll cap the plasma current. There you go. It's not so high, right? But the physicist knows that, oh, well, that interacts with all these other variables, and this is how I would make it not do that, and that's it.
Very general question. In your assessment, or what would be your guess for how many years we're away from the fusion of the energy source?
Yeah. We're in a weird spot right now because there are VC-funded fusion companies that had to basically make some pretty unrealistic things about how they'll deliver electricity to the grid, including one that said, I think, not going to happen. Actual fusion power on the grid. If I was going to make an optimistic estimate, I might say something like 15 years. And if things don't go well, it could be much longer. What's happening right now is the fusion companies are setting up not even demonstrators, really prototypes, where they're trying to show they can get more energy out than they put in. If those go well, then they would build a next generation, which would be a demonstration power plant.
Are you pretty confident that it will happen? Like in the next?
Oh, it will happen. The progress has been tremendous over the decades, and there are hard problems left, but we're not at the point where things might be physically impossible. They're just hard problems.
Does your framework apply to stellarators?
We wanted to do Bayesian optimization for stellarators because a lot of the work is in the design in advance for the shape of things. And so, I think you can do pretty good simulations of some of the things you want to do, but they're expensive. But the number of operating stellarators is pretty small. So we believe that Bayesian optimization, some of the stuff I showed toward the end, would be ideal for stellarators.
All right, that's about it. Let's get one more round of applause.